Okay, welcome everyone. Thank you for having me here, and thank you for the organizers for inviting me here. It's a wonderful occasion for me to come back to Stanford after COVID, after a little bit of time. And today I'm going to talk about a topic that I'm very fond of and excited about, which is tactile sensing. And I will go through different aspects of touch, why it's an important topic, and going from the perception to the understanding, and ultimately how do we use touch for interacting mostly through robots. And just to give you a little bit of background about me and what are my interests, my background is at the really conjunction of machine learning and robotics. And a lot of the research that I've been doing the last few years have been motivated by the fact that in the last decade there has been really impressive development in the use of machine learning and applying this type of techniques to a really large number of fields, including some pretty impressive reinforcement learning on games and on robotics. And some of the questions that I'm generally interested in asking is how do we scale this type of algorithms to more complex real-world applications? What are the really the aspects that requires to be improved algorithmically so that we can ultimately achieve impressive results in fields like robotics, decision-making, finance, biological science, and such. And in this talk, I'll be focusing mostly on robotic, which is my main field of application of the algorithms that I developed. And the reason why robot, I think it's a little bit self-explanatory, but for me, what robots can bring to our society, the benefits that robots can have are huge. What I would like to see in 10 years, 20 years, is robotics everywhere in industrial automation. I want to replace every single children mining coal in Thailand with a robot that can do this without having to break their bones over endless shifts of work. I want to be able robots to help with disaster relief, with all of the weather changes that we have nowadays, which are getting more and more violent. I want robots to be able to explore the world, both the underwater world and other planets. It's very likely that, we already have actually seen this, that the first human artifacts on Mars are not people, are robots that we can control from thousands of miles away. And finally, medicine and elder care. With the growing elder population that we have in westernized societies, it's becoming more and more important to be able to provide robots that can help and assist elders and general population. However, if we look critically at what is the state of robotics, these are some videos from the DARPA competition in 2015, and just to give an idea of what we are looking at here, these are the best team in the world. These are teams that spend 2-3 years, in some cases with hundreds of people, working extremely hard on having robots going through different paths and tasks and challenges. And the type of errors that we see, the type of failure modes that we can observe in this type of very sophisticated robots are failures that we would never associate with the word intelligence. It's not the type of failures that we would never associate with, even kids. My 3-year-old kids will never fail like this in a way that, for a human is stupid, So what are we missing? Why is, how can we help robotics through the use of machine learning and artificial intelligence? And even more, what do we need in order to be able to eventually, ultimately have meaningful interaction between, humans and robots in a safe manner, in a way that is interactive, really. And I believe that there are many challenges that we will have to address over the next decades. And these challenges are really all over the spectrum, from hardware design all the way to control, software, and ultimately reasoning and planning. And some of these aspects that I'm personally sort of interested in are things like multimodal sensing, optimized hardware design, and quick adaptation to new tasks. And all of these fields are different sort of source of inspiration for my research. But in this particular talk, I'll be focusing almost exclusively into touch sensing as a way to address the lack of sensing that current robots have, and as a way to explore the multimodal nature of interactions that we as humans have. And just to reiterate, or maybe to get started really about touch, touch is a crucial sense in our everyday life. We might barely realize this because we are very much used to it and we give it for granted, but every time that we grasp an object, we actually are extensively using our sense of touch in order to measure contact forces between our body and the world around it. We are estimating object properties. We are estimating a lot of information also about how the different forces are balancing. And ultimately, in a world where dynamics is everything that matters as we interact with the world through forces, it seems very unnatural, the fact that our robots are currently not able to sense force in the first place. And if we want to be able to accurately sense forces and to control them, we need to have robots that are able to perceive the world through touch. And here is a very famous video from the department of Ronald Johansson, where they would essentially ask people to do very simple tasks, like lighting a match, and then they would anesthetize their sense of touch while keeping their motor control capabilities. And what we can observe is that humans, all these subjects, would immediately lose the capability of doing this very trivial task. And this is really an indication of how heavily the motor control policies that these people are using actually make use of touch, and how hard these tasks are without. Now, touch sensing for robots or as a digital sense is actually a really hard task. And there are several reasons why this is the case. The main one is really the fact that it's a very interdisciplinary field by its own nature, because it requires a vertical integration between all the way from what is the hardware substrate that we use to sense touch, and then how do we make sense of it, and how do we integrate touch in a control loop, which might traditionally use only perceptive information or vision, and ultimately in which application do we deploy it. And what historically has been happening is that different labs have been focusing at different levels of this vertical integration, but has always been very difficult to integrate these different levels, has been historically very difficult to reuse solutions that were often ad hoc to build on top of this something that is more meaningful. And effectively, this leads to having a lot of labs that do amazing work, but that keep reinventing the wheel over and over again, because nobody else is going to then make use of what they built to do something more. And this also leads, from a practical standpoint, to a very high entrance bars from new researchers, because you need to be able to, in many cases, to build your own sensors if you want to do research on this, or you need to be able to have a very large set of expertise if you want to be able to use prototypes of somebody else. So one of the fundamental questions that I'm going to try to answer with this talk today is, how can we lower this entrance bar? How can we improve reproducibility in the field and ultimately accelerate research by reusing existing components that different labs can build, innovate, and create? And all of this will point to the fact that as a community of touch sensing, we need standardization, and I will very strongly argue for the need of creating an ecosystem of tools that can be openly used and accessed and built upon from the whole research community. And to give a little bit also of a way of how I frame internally to myself and to the people I work with this type of work, I want to give a little bit of a historical perspective. The way that I think about touch is not only as let's give a robot touch, but it's really as creating a new field of digitalization of touch as a sensor modality. In the same way that at the end of the 1800s, the mass availability of telephone for the first time enabled people to essentially record audio, transfer it over long distances, and then play it back on the other side of the world. This created the opportunity for new fields of computational science, like audio processing, and more recently with the boom of AI, natural language processing. And this has given incredible type of abilities to our machines nowadays, that you can talk to it and they understand what you actually mean. And a similar trend has been enabled in around the 1990s with the first mass production of digital camera sensors. And again, having cheap, reliable sensors enabled the creation of a field of computational science dedicated to making sense of vision, ultimately fields that are extremely successful, like computer vision. And every one of you nowadays has, for sure, cameras in your pocket, in your phone. You have tens of them probably around your everyday life. And this enables, again, to cheaply and reliably digitize images, transfer them over distance, and essentially replaying them back onto a screen. And I believe that now, in this decade, we have the possibility of having a similar path for touch with the first cheap, reliable, and mass manufacturable digital sensors for touch. I believe that what we will see in the next decade is really the building of a new computational field of computational science dedicated to make sense of touch, dedicated to be able to digitize touch, record it, transfer it, and replay it back on the other side of the world. And this will ultimately lead to, I believe, a lot of wide-scale applications into our societies. And I will very briefly touch on this later on in the talk. So given that this is the way that I try to frame what we are really looking at with the research on tactile sensing, what are the important aspects that in practice we need to implement and we need to execute on? The 4 pillars that we identified and that we typically like to think about are for making touch sensing practical in the real world are hardware, the fact that we need to have good hardware which is reliable, which is cheap, which is able to sense the things that we care about. Once we have this, we need to be able to process this data. We need to be able to extract information. We need to be able to make sense of touch by processing. And I will mostly speak in this talk about the use of AI for processing this type of inputs, because this is where what I'm interested in, and because of the specific type of sensors that I'll be talking in this talk. And then simulation. Simulation is generally a very important part of any scientific discipline. Benchmark and dataset is also very crucial, because in this moment we don't have good benchmark for touch. We don't have large-scale datasets which are widely available, and these are very important stepstones for the growth of any scientific community. And finally, I will be talking about applications of touch in the real world, and a little bit about community, which is something that I'm very fond of, and I think it's very, very important. But let's start from hardware. Hardware, tactile sensors in robotics, is a field that has hundreds, maybe thousands of sensors out there. Mark probably has made hundreds of them in different ways alone. But essentially, we can see that there are, if you look at the literature, there is really a huge plethora of potential tactile sensors. But what is, I think, a failure point here is the fact that the large majority of them always remain at the stage of prototypes. A lab spent a couple of years, bunch of time and money on building a sensor. You build one, perhaps two, and once the project is done or the PhD is done, you take it, you shelf it, and that's it. This technology is never going to be used ever again. And this is it's a huge pity, and it's also a huge waste. And this leads to the fact that from a commercial point of view, if you want to buy tactile sensors nowadays, there is an extremely limited choice. There are probably 3 or 4 sensors that you would seriously consider, and most of them are probably more expensive than you can afford anyway. So this is a big problem from hardware perspective, and this hampered the whole vertical stack, because without reliable hardware, it's very hard to do anything else. Now, the important factors typically in deciding tactile sensing hardware, or the way that you can classify hardware, are a few. The first one is, of course, availability. You want to have sensors which are widely available, that you can buy off the shelf without having to wait a long time. The second one is cost. Cost of tactile sensors can be very diverse, but in many cases, it's very expensive. Form factor. You might want to have sensors that is flat and look like skin, or you might want to have sensors that are more like fingertips, or anywhere in between. And this form factor play very often an important role in the specific applications that you might care about. Finally, capabilities. What is this tactile sensor measuring? What are the type of output that you will get out of this sensor? Some sensor will only return to you normal forces. Other sensor will return you numbers that are not even, don't even have a physical meaning. And we will see that some of them return to you images. So what are you getting back? What is the resolution? What is the frequency? And so on. And finally, reliability. Unlike digital cameras, unlike telephones, in the moment when you have a tactile sensor, this tactile sensor will inevitably incur into a huge amount of wear and tear, because literally every sampling that you are taking of the world around you will ruin the sensors because you are applying forces and you are somehow breaking it. So how do you make a sensor that can withstand thousands or hundreds of thousands or millions of interaction? And the solution that we have in nature is amazing, is that we have self-healing fingers that grow back if the skins get scratched. Well, we don't quite have this type of technology yet in tactile sensing. So the type of sensors that I'm going to discuss today more in depth are the so-called vision-based tactile sensors. And I want to give you an intuition of what is the principle of how they work. The idea is a fairly old idea. It was actually proposed several times in the 80s. But it's very, very smart. The idea is that you want to have a camera, which can be a normal cell phone camera, which is essentially looking at a piece of silicon or an elastomer. And then you have structured light, typically RGB colors, that are shining onto this elastomer. Now, whenever you're touching this elastomer, this will create deformations internally in the way that the light is reflected back to the camera, and will, in practice, create shadows of different colors depending from the geometry and the force that is being applied to this elastomer. And this is an extremely cool technology because it has virtually no moving part. The silicon is the only moving part, which solve a lot of the problems about reliability of the wiring, about reliability of the electronics, and the manufacturing, because it's very easy. We know how to manufacture a camera at scale. Now, what we did in 2020 is that we open sourced the first mass-producible, miniaturized, high-resolution vision-based tactile sensor. And this is how a digit looks like. This is a sensor that was designed from the scratch for democratizing touch, in the sense that we wanted a sensor which is easy to manufacture. You can actually 3D print it at home. Everything is online available, so you can literally go home, 3D print it, buy a piece of electronic from a standard PCB way, plug it in, and this sensor will basically work. Now, this was essentially designed to be cheap, reliable, mass manufacturable, and really accessible to anybody. This was our intention. And the type of sensor readings that you get out of digit is something that looks like this. So you can see this is, for example, a piece of Velcro, and you can see the individual teeth of the Velcro. So the spatial resolution that you get out of digit is about 15 micron, which is fairly revolutionary if we compare to traditional technologies for tactile sensing, like capacitive sensors. And although you get these strange patterns of light, you can effectively see a lot of details. You can see a lot of really nice things. And you also have this nice sort of 2D style of image, which we will see is actually very advantageous for processing after using machine learning methods. And just to give a curse comparison against the leading commercial product, which is the biotech and the digit are both miniaturized sensors that can be mounted on a multi-finger robotic hand. But the biotech has 29 or 19, depending from the model, point of contact. So sort of, you can think of this in terms of pixels of resolution. While the digit has about 3 orders of magnitude more. And at the same time, if you want to buy a biotech, this is going to cost you $15,000, while building a digit is a fraction of this. It's effectively 3 orders of magnitude more data for 3 orders of magnitude less money, which is pretty great. And our digit is also open source, so anybody can download it, anybody can modify it, and you can build it at home. And so far, the most interesting things for us has been that over a dozen to dozens of universities have actually reproduced these sensors on their own. But we also partnered with the GelSight Inc., which is a startup in Boston, to actually have the sensor commercially available. And you can effectively go to their website and buy it, and it's shipped to you at home without any need for expertise knowledge on how to 3D print things, if this is not your thing. And overall, in the first 10 months, we sold over 1,000 of this sensor, making it the most widely available tactile sensor in the robotic world, which I think is pretty great for a sensor that costs $300. So after we have the hardware, let's move on to simulation. Simulation is generally a really important topic for any scientific fields, because it allows you to play with things. It allows you to benchmark your algorithms. It allows you to measure progress and doing fast prototyping. However, what we see in traditional simulators is that it's very hard to simulate something like a vision-based tactile sensor, because typically the more contact points you are trying to simulate, the slower your simulator will get. And already with a few hundreds contact points, a traditional simulator like Gazebo will essentially go much slower than real time, making it the simulator sort of defy the purpose of being a simulation in the first place. So what we proposed and open source actually last year is a new type of simulator, which we call Tacto, which is explicitly designed for simulating vision-based tactile sensor. And by making a couple of smart sort of adjustment under the hood, we can actually simulate fairly complicated scenarios at hundreds of frames per second while still getting high-resolution images of how the contact would look like. And the nice things about this simulator is that, again, it was designed to be open source, so it's publicly available, but it's also modular. So it can be, in theory, integrated with any physics engines of your choice, whether this is Mujoko, PyBullet, or Isaac Jim, and at the same time can be integrated with different sensor configuration. So if I now build a new sensor with a completely different shape, it's in theory possible to just write a configuration file, plug it in, and have it simulated. And here, for example, we have some simulation for a digit sensor, and this is another sensor called OmniTac, which is actually ping the real sensor. This was not, something that we hard-coded. This is actually something that naturally rises because of the distribution of lights, which is pretty cool. And the nice things about the simulator is that it's actually fairly realistic. Not completely realistic, but if we compare images from the simulation and from the real sensor, it's qualitatively there. I would say that it's kind of okay. For something that, again, can run at hundreds of hertz per second, this is great. This is what we want. Fast, maybe not accurate, but good enough. So once we have the hardware and we have a way of simulating this hardware, what we care about is processing. How do we make sense of all of these images? How do we make sense of this huge amount of data that we are getting from our sensor? And this is a very tricky problem. And this is, I believe, the crucial points that will differentiate the efforts that are going nowadays on in tactile sensing compared to the past. Is that once we have standardized the hardware and the simulation, we can now focus on how do we make sense of this. And really, what I'm aiming at is the fact that we will have to create a new field of computational science, which we call touch processing, whose goal will be to make sense of touch. And some of the questions that we will have to deal with will be questions like, what type of features do we want to extract? What is the equivalent of a SIFT feature that in computer vision are widely used for touch? We had a discussion with Mauro before about, should we use images? Should we extract optical flow? Should we use stress fields? What are the meaningful representation for touch that can be also generalizable between different sensors? And even more, what are the computational structures that we can exploit for processing touch? In vision, we know of the 2D structures that we have in an image. In audio, we know of the temporal structures that we have in audio and sentences. But touch is more than this, because it incorporates both structural information, where we have a 3D world which is mapped through a 2D manifold that we are sensing. We have a temporal structure where vibrations and slippage is heavily influenced over time. And we also have multimodality, because our skin is actually made of many different senses that we are integrating. And again, touch is a local sense where we we can measure what we are touching. So it's much more active as a sense compared to vision, which is instead global because it gives you global information about what you're seeing. But it's virtually passive because you have no way of influencing directly what you're looking at, or at least not really. So all of this will result in a number of questions which are, as of today, unanswered, but that will be crucial in making touch practical and useful in the real world. And as a first step toward trying to answer these questions, we also open source a library which is called PyTouch, which is the first library dedicated to essentially touch processing using machine learning models. And the idea here is that we want to create what is the equivalent of OpenCV, but for touch rather than for vision. We want to have a tool which can be where every practitioner goes to, which is easy to use, where people can attach different type of sensors as an input to a standardized interface, and where they can then go and use and provide to the community different models that provide different functionalities. And once we have this, then it becomes much easier to really starting to explore questions about, is this sensor better than this other sensor? Is this model better than this other model? And really comparing things which are apple to apple. So I will skip over some of the features of PyTouch. The only one that I want to point is the fact that we see PyTouch as a service. It's the fact that in this moment, if you download PyTouch, you get a digit, you plug it in USB, you download PyTouch, and you can, with 2 lines of code, you can essentially just define, I have a digit sensor here connected, and I now want a model which detects if there is touch. And PyTouch comes with pre-trained models that you can directly download or are downloaded in the background if you just request this. So now having a sensor that can directly give you functionalities in 10 minutes after you unwrap it, it's actually possible through a smart use of standardized hardware and standardized software. So, and this sort of start to also enabling us to ask scientific questions. And one of the scientific questions that we, mostly as a curiosity, try to answer in this work is whether, for example, we can learn features that are generalizable across different vision-based tactile sensors. And the idea is that if we use 3 different tactile sensors, like Digit, OmniTac, and GelSight, and learn a pre-trained model, using this pre-trained model to then identify, having a task like touch detection, will yield to better performance compared to only using data from that particular sensor that we are using at deployment time. And this is really cool because it really starts aiming to some of these questions of what is a generalizable features for touch? Is there even such things as a generalizable features of touch? And the answer seems to be that, yeah, probably there is, because a joint model does better than something that is trained only on that particular sensor. So finally, the 4th pillar of our ecosystem is benchmark and datasets. Benchmark and datasets are crucial for any healthy scientific community. They are extremely important for measuring progress, are extremely important for being able to, with the dataset, also provide tools to people that are not interested in working exclusively in hardware. And so far, it essentially has been a desert, in the sense that we don't really know what are the benchmark. Different papers evaluate sensors in different ways. And in many cases, these are not standardized benchmarks that are easy to reproduce. And at the same time, there are very, very, very few data sets that are publicly available. And this means that it's extremely hard to evaluate models or to really make use of any of this data that other people collected. So these are 2 really important topics, and I hope that in the future we will be able to make progress in these fields a lot more. But just one of the very small contribution that we did was that together with the release of our simulator Tacto, we also released this standard benchmark for predicting grasp stability, where the idea is that we want to be able to detect whether this object will still be in my fingers after I raise it. And we can now do this in simulation, and more importantly, we can do it at a scale which is unthinkable in hardware, because we can now collect millions of grasps of an object in simulation, and this is qualitatively different than being able to collect 5,000, which is the largest data set that has been collected in the real world. It allows us to test hypotheses and to train models in a qualitatively different way. And this is really just, I believe, the start of having more benchmark also in simulation. So at this point, I will switch over and spend the last 10 minutes talking about applications. I believe that touch is going to have a really important role in a very wide range of applications. And some of the ones that I'm personally most interested in include things like prosthesis. If we are able to sense touch, we can give people that lost their limbs the capability back of being able to sense the world around them, being able to grasp objects better, being able to walk more stably on different surfaces, and so on. And I think that this is already worth it just for this. But there are, of course, also other fields of applications. There is this whole idea of the metaverse, where you want to be able to also physically interact over the distance with different people, whatever that means. You have applications, potential application in e-commerce, In the same way that nowadays you can take a picture of an object and say, hey, search for this object, I want to buy the same one. I hope that one day we will be able to take a digit, touch a sweater and say, hey, buy me an object which has the same thread or the same softness as my sweater. Or maybe you will be able to touch your skin and say, hey, can you suggest me what's the best beauty product for my skin, or things like this. Anything that can be measured physically, it's likely to be commercial applications for a tactile sensor. And finally, robotics, which is, of course, where my heart stands, and I believe that robots very heavily need touch in order to be able to do a lot of tasks. And specific tasks in robotics, which I believe are important, are things like agricultural robotics, where there is really no need. Like strawberry picking is still done entirely manually because strawberries are fragile, and with traditional robots you would just squeeze the strawberry and make it unusable. If we could use tactile sensor to be more gentle in picking strawberries, and we know we can, why don't we deploy this instead of having people essentially having to quit after 5 years because of their back for bending down and doing strawberries picking. And medical robotics, where in a lot of applications for a telesurgeon to be able to sense the tissue that you are cutting or be able to sense if there is cancer or not, these are still very much manual operations. And if we can digitize the sense of touch, then it's very likely that we can also digitize some of these specific tasks and applications. Breast cancer, why not using tactile sensor for doing this automatically instead of having to rely on expertise, human expertise. And just spending one word on touch for the metaverse, I want you to realize how touch is effectively the most social and emotional sense that we have in our life. There is nothing that is equivalent to be able to, hug a loved one or touch a loved one. And the fact that we are not able to digitize it, it's a very big limitation over what is possible in terms of being able to convey emotions in order to be able to convey different state of minds. So some of the questions that I'm broadly interested in is how can we sense, calibrate, and reproduce touch over the distance? And really here, the contributions that we have been, that we can provide as a basic research team is on the first part. So how do we essentially collect sense, and how do we make sense of this? I don't work with optics at all. I hope that somebody else will, and will, have digit on the other side of this. And just to give one more word about this, actually in 2015 we had a fun paper with some students of mine at the time, where we were using tactile sensors, very primitive at the time tactile sensors, to provide haptic feedback to a glove, which was used in a system for first-person teleoperation. So we essentially had an Oculus Rift, where you could see through the eyes of the robot. You could control the neck movement through just your head. And then you had a Kinect for detecting the pulse of the person and mapping it onto this complex humanoid robot. And then through the haptics, you could feel the sensations of what you were touching. Although in our case, we had very primitive haptic feedback because we were just using vibration motors to essentially provide different levels of forces. So, and as you know, vibration motors are actually really a bad idea for providing haptics because humans get used to vibrations. So after a few seconds, you don't even perceive that it's vibrating anymore. But it was a funny application, and this was almost a decade ago, so long time. Anyway, finally, robot learning. This is what I'm actually mostly working on nowadays. There are plenty of applications of really at the conjunction between use of touch, machine learning, and robot control. And some of the kind of things that we've been doing in the past is to be able to predict if a grasp is a good grasp. before lifting, before applying vertical force, is this going to be a reliable grasp, or is this object going to fall down? And once you decide that this is maybe not a good grasp, how do I adjust my fingers so that I have a grasp which hopefully it's more robust and more reliable? Also learning multimodal representation, which can transfer from vision and touch. As a human, so if you look at an object, you can guesstimate fairly well how this is going to feel when you touch it. And vice versa, if you're blindfolded and you touch an object, chances are that you can estimate how this is going to look visually, and potentially also, mechanically, what's the material you're touching and so on. And then also reconstruction of surfaces, both from just touch and vision and touch. But one application that I think it's kind of funny that we did more recently, and we are going to present this in Japan in next month, is actually using touch for learning how to play piano better. If anybody of you play instruments, you know how important is touch in being able to modulate sounds in your instrument. At least in piano it's important. I used to play cello. I can guarantee that also with cello it's important. So we essentially use in simulation our tactile sensors to be able to play scores better and better by being able to modulate intensity, force, and time better. It's just in simulation so far, but I would love to see this on a real robot one day. Also, another application which I think it's very cool from 2020 is being able to manipulate small marbles, glasses. This is a task which seems, for humans it's relatively easy, but for robots it's actually extremely hard. And the reason is because you need at the same time being able to move a marble between your two fingers, but you also need to be able to modulate the force between them and the marble. So, because if you apply too much force, the marble will be squeezed out from its position. If you apply too little force, you will lose the marble because of gravity. So you need to be actually doing very, very fine manipulation at the border of friction that actually allow you to move and keep the ball between your fingers. And in order to do this, we actually used fairly advanced machine learning algorithms. Specifically in this paper, we used a model-based reinforcement learning algorithms, where we were taking raw images from the sensor, and we were essentially learning a latent space, or feature representation, if you are a deep learning person, and then use this for making predictions into the future by learning a forward dynamics model. So now, given the two readings from the sensor, we were able to predict that if we were to apply a particular type of movement to my fingers, this is how the next image will look like. And once we are able to have this forward dynamics model, which is, by the way, also how humans work, we are able to essentially plan what is the best set of actions in order to reach our desired goal. And this actually worked very well. And more importantly, it worked from raw images. So we completely sidestepped the problem that a lot of tactile sensors have, that they need to be calibrated. Here, the robot does not have an explicit idea of the concept of force, but through the dynamics model, through the reward, it's able to learn what is good and what is bad in terms of raw pixels. And the fact that, if you lose the marble, well, that's bad because you don't have the pixels moving in the right place anymore. Ultimately, I believe that all of this line of research on tactile sensing and manipulation for robotics will ultimately lead to have, or I hope will lead to have dexterous manipulation types of skills which are on par with humans. And I think that the path is still very long, but I hope and believe that this is reachable in the next decade or so. So fingers crossed, which for robots is also very hard. So to conclude this talk, the other effort that I mentioned briefly and we care deeply about is community. If you are interested in tactile sensing, if you are working on these fields, We do have a website and a Slack channel which is available for all researchers. And if you're interested, I would encourage you to register. It's really a space where researchers can share information, can share cool results, and can just discuss with other people from the same field, which I think is very important. I, of course, want to thank all of my collaborators that have been working with me over the years. These people are extremely important in my life. I loved working with all of them, and sometimes it's underappreciated how important good collaborators are for one's life. So to conclude, and this is not the full set, unfortunately. There are more that, In particular, I would like to point out Mike Lambetta. He has been, he is my partner in crime for everything concerning Digit, and he's, our expert hardware engineers on tactile sensing. So really important person. So to conclude, I hope I convince you that touch is a crucial sensor modality in both humans and robots. And throughout the last years, our goal has been to try to create this standardized ecosystem that can help researchers to do research faster, that can enable people to join the field in an easier way. And in particular, we have been open sourcing a number of tools for hardware, cheap and reliable hardware, fast simulation, and touch processing. And we really have been trying very hard to build all of these tools by consensus, by talking, interacting, and trying to support the community, because we deeply care, and I deeply care as a scientist, in really supporting the scientific community and growing it in this field, which is just now getting at the beginning. And my personal long-term goal is to make touch sensing more practical and more accessible, both for researchers and in the real-world applications. So thank you very much for your time, and I'm happy to take questions.
Roberto, I had a question. So I think it's really interesting, the idea of having multimodality through tactile sensing. And I was wondering, for the Digit or such vision-based sensors, how do you think we could have multimodality in the sense that maybe have, besides the high spatial resolution, have like higher frequency signals as well? Because as you pointed out, we are very multimodal.
Sorry, I cannot hear you. Can you?
Oh, sorry. My question was, how can we enable multimodality for tactile sensing and in platforms like Digit?
Yes.
You mentioned that Digit is a very high spatial resolution, but how can we include the high frequency signals that humans also have? Yeah. I think that would be pretty cool.
Yes, I absolutely think this is crucial. I think that current Digit, the fact that it's not multimodal is a very big limitation. To be honest, it's a big limitation of any sensor that is out there. The only sensor that I know that is to some degree multimodal is the BioTAC, which also incorporates frequency readings. I absolutely think that this is the path to go. When it comes to Digit specifically, you will have to wait for Digit 2.0. Yeah.
Another question. You're here still, so you have questions. Yeah.
And vibrations, in particular, are really important for a lot of dynamics manipulation. So I think that should be a very high priority.
So I was kind of curious, with the image-based touch sensing, that doesn't seem very intuitive to me. Was that the easiest setup for you guys, or what's the advantage there instead of using force sensors and things like that?
So first of all, I agree with you that vision, this type of images that you get from a sensor, are not as interpretable, or at least are not characterized with meaningful physical principle like forces. However, from a high-level point of interpretation, sorry, this is way back. It's kind of interpretable because you can see edges, you can see shapes, which humans are actually fairly good at understanding intuitively. If you, if you look at this image, you can extract some type of information about the geometry. It's true you have absolutely zero idea, was this pressed hard or not? That's an educated guess, not really. But the geometric part is actually fairly intuitive for humans. Now, sorry, what was the other part of your question?
I was kind of asking what was the advantage of...
Oh, yes.
Yeah.
Sorry, I'm getting old. The big advantage is the fact that you have unprecedented resolution. A traditional resistive or capacitive type of sensor would probably be a grid of maybe 100, maybe a couple of hundreds pixels in the same space. While here you have 300,000. You can do a resolution which is 3 order of magnitude higher than other type of technologies, and at a fraction of the cost, because this is extremely cheap to produce, and it's extremely reliable in the sense that a lot of these other type of technologies have moving part where you have cables, you have wires, which over time break. This thing, what can happen is that you break the silicon, and in the design of our digit, the silicon is solved by one screw. So you break the silicon, well, too bad. I throw this away, I put another one, and I can keep collecting data in 30 seconds. If a resistive capacitor sensor break down, chances are that you need to change the whole electronics. So these are some of the, in my opinion, very big advantages of vision-based tactile sensors. Resolution, manufacturing, reliability, these are pretty big items.
Thank you.
Maybe another one which is not so much highlighted is that also the sensitivity of vision-based tactile sensors can be much higher than a capacitive or resistive sensor, because effectively you can tune the bandwidth, the dynamic range of your silicon based on the application. So I can make today a piece of silicon that is able to sense micronewtons, and then tomorrow I need to pick up oranges, and I'll instead make a very rugged piece of silicon which is in the order of hundreds of newtons. And all of this can be done just by, again, changing the piece of silicon that you have.
In terms of data sets and benchmarks, do you see an advantage in developing a data set of video touch data that perhaps could be helpful when you're doing model-based reinforcement learning and predicting the future states with how the dynamics work?
Yes, absolutely. I think that a lot of the really interesting tasks that we should be able to do with touch are actually dynamic tasks. Being able to rotate an object in your hand, is be able to throw something and pick it up or whatever. And all of these tasks that requires dynamics are of course better suited for having temporal type of data. So having just one image is okay for, if you want to detect what material you're touching or what you're touching, but it's not very interesting from a robotic perspective. There is no dynamic there. And for everything that is dynamic, then also the frequency of your sampling becomes important. And in order to truly be able to close the loop, also the decision making becomes important. So how fast can I make a decision based on what I'm reading from my finger? And when I was working here with Rohan, we were actually discussing that humans have, for example, a reflex arc, which is extremely cool because if you touch something that is hot, your finger will retract within about 20 milliseconds because the signals goes to your spine, and the spine essentially just activate a reflex before the signal even reaches your brain. So your finger is already back before you realize, oh, this is actually hot. So being able to do this type of closed loop, fast decisions with touch, I think it's mind-blowing. It would revolutionize the way that we do manipulation.
Thank you.
Thanks for the amazing talk today. I think today's talk was mainly focused on sensing on the fingertip. I'm curious what your opinion is on the importance of sensing on areas outside of the fingertip, say back of the hand or the arm, and how scalable and modular sensors on those areas can look like.
Yeah, excellent question. The way that I see it is, the two are complementary. In the same way that humans, as humans, we have more sensitivity in our fingers than, let's say, in our back or in our forearm, but we do need both. And in robots, I believe that this is also the case. Ultimately, what the golden grail would be is to have a robotic hand where you have very sensitive fingertips if you want to interact and sense, but also to have the full palm and the full arm and the full body of your robot fully covered. The way that I see it, the challenges are a little bit different, because in the moment when you are talking about skin, there is much more of a problem of scale. How do I build a skin with millions of contact points without having to have millions of cables? And this type of vision-based technology, I think, would be amazing if we could adapt it to skin. But if we look at the technology today, it's not suitable because of the focal distance between the camera and your interface. This would give you a depth of about 1 centimeter, which is more than you want for most artificial skin. I should point out that in Meta AI, there is a line of research also on tactile skins. So Tess Hellebrecher has been leading work on Reskin, which is a cheap, sort of low-cost, again, type of skin for whole body sensing. So I see this as complementary that should eventually be put together.
Thank you.
Hi, thanks for the talk. I actually have a very similar question. So it's also regarding the mechanical aspect of the digit sensor. Just wondering how scalable it is, and then what kind of disturbances, like temperature variation, all those kind of stuff, would it affect the force sensing accuracy of the sensor? Would you think scaling it up, let's say to a surface, and then maybe installing it to a payload for payload transportation? Is that a possibility?
So if with scaling you mean making it bigger?
Yes, area, in terms of area.
Yeah, that's actually the easy part. In the sense that in many cases you can just change the lens, change the camera, so that you can cover a larger range of surface. This is actually pretty easy, and GelSight, the company, the startup in Boston, they actually started from tools that were for large areas, and the hard part of this type of vision-based technology is actually the miniaturization mostly. Sort of just to give you a very simple idea of how you could scale this, if you just take this sensor and now you put 10 of them in parallel, they are all USB. You can just connect all 10 of them, and now you have a sensor which is 10 times the dimension. Now, I'm not suggesting that this is practical. What would be easier is just to move the camera a little bit farther away, which will increase sort of the space that you're looking at, and you can do this.
Okay, thanks.
Yeah, thank you for this eye-opening talk, at least for me. So I do like your example where you say that in the future maybe I can ask my sensor to say that buy this clothes as smooth as this one. So then I realized that there is something that I don't quite understand. is that it seems that for smoothness, right, I can see how this vision-based sensors can sense like a normal pressure. But for smoothness, a large part seems to also be like friction, right? Like kind of whether it's like low friction or high friction. I wonder what's the like state of art on the like tangential force like sensing in this area, and like maybe what's your group's plan in this direction? Yeah.
Yes, this is a very, very good question. For a lot of manipulation tasks, shear forces are actually what you really care about. If you're manipulating objects. Now, the way that this vision-based tactile sensor perceives shear forces is through a couple of different mechanisms. One mechanism which is very popular is that you can essentially paint markers inside the silicon, and as you apply shear forces, essentially these markers will move around because of the deformation of the gel. This is an approach that, for example, Ted Edelson at MIT uses extensively, because once you have these markers, then you can compute optical flow, and you essentially work in this field of optical flow, which is computing shear forces. Another possibility, which we briefly discussed, is that maybe it's actually not even necessary to use optical markers at all if you have texture, some sort of texture in the elastomer layer, and then you can directly look at the texture. So one example is that if you 3D print the mold of this silicon, the texture of the 3D printed part will actually impress some very specific pattern on the way that the light is reflected back. And just by looking at this, how this texture moves, you can compute shear forces.
Thank you.